Hi, everybody. I want to quickly talk to you about relative velocities, which is an interesting concept in physics. It's super useful and also really cool. So relative velocities, think of it this way. Let's say you're in a car, the car is going at 50 miles an hour, and you turn to your friend who's in the car with you and you say, am I moving? And a natural question that they would ask you is like, well, with respect to what, right? Or they'd say no, or maybe they'd say, of course, you're moving at 50 miles an hour. But really, there's a lot of answers to that question depending on with respect to what. For example, relative to the reference frame of the ground, you and your friend are moving 50 miles an hour. Relative to one another, you're not moving at all, right? You could toss a ball back and forth between one another and nothing's going to happen, right? That ball isn't going to move anywhere. It's going to just stay with you. But relative to someone on the ground that you're passing, you guys are flying by, right? So relative velocities are important because you technically always need to specify with respect to what. Now we don't do that. We assume everything's relative a lot of times just to the reference frame of the ground. But even then, the Earth is orbiting the sun is moving in our galaxy is moving through space. There's a lot of layered motions, and a lot of times we give our velocities relative to the surface of the Earth, ignoring the fact or choosing to, ignore the fact that the Earth is actually rotating. All right, so let's think about relative velocities. I'm going to write them up here. Let's start with a simple example because it sets up how you deal with them, and then we'll get progressively a little bit more complex. Let's say you're on one of those things at the airport, that little baggage things that you can walk on, those little moving walkways. And let's say we have the velocity of the walkway relative to the ground is 2 meters per second that way. Now let's say you're up here and you're moving and you have some velocity of u, I'll use a y for u, relative to the walkway. And then let's say somebody also sees standing over here is just watching you go by, and they see you go by the velocity of u relative to the ground. How are all of those three things related? Well, it kind of makes sense if you think about the velocity of u relative to the walkway plus the actual velocity of the walkway relative to the ground is going to overall give you your velocity relative to the ground. And that's exactly how it works. It's like the transitive property. If A equals B and B equals C, then A equals C. U relative to the platform plus the platform relative to the ground is U relative to the ground. So let's say you're walking relative to the walkway at also, let's say 3 meters per second that way. Well, then we could say velocity of u relative to the walkway plus the velocity of the walkway relative to the ground is the velocity of u relative to the ground. So 3 meters per second plus 2 meters per second, and you guessed it, you get 5 meters per second. So you seem to this person on the sideline like you're moving really fast because relative to them you are. Some of your velocity is relative to the platform, and then the speed of the platform adds to your velocity. Let's say you reverse and you decide to walk in the other direction at negative 2 meters per second. So instead, the velocity of u relative to the walkway was negative 2 meters per second, but the walkway relative to the ground was still 2. Well, that would mean you were stationary relative to the ground. And that's like what happens on a treadmill, right? The treadmill's going this way, you're running at the same speed, but in the opposite direction as the treadmill. And those two velocities cancel and you stay stationary relative to the ground. This is a really important relationship, this transitive-ish kind of relationship, because it's going to guide you when things get a little less straightforward. Let's look at another example, this time a two-dimensional example. Let's say there's a river, and we have the velocity of the river relative to the shore, the ground is, let's say, 2 meters per second that way. I already said that way. Now, let's say we actually have a swimmer, and we have the velocity of the swimmer relative to the river is going to be 6 meters per second. So they know they're a swimmer. They know when they swim in a pool, they can swim 6 meters per second. So they're going to set out to do that across the river. But meanwhile, the river is flowing at 2 meters per second sideways. what's going to happen? Let's see if we can use our relative velocity equation, but now we have to use it as a vector equation, not as just numbers that we can add and subtract. So the velocity of the swimmer relative to the river plus the velocity of the river relative to the ground is going to be the velocity of the swimmer relative to the ground. But now we have to, it's not a straight addition, we have to combine these as vectors. So let's do that. Velocity of the swimmer relative to the river, which is 6 meters per second up. And then we have the velocity of the river relative to the ground, which is 2 meters per second to the side. And when you combine those, we know how to do this from our work with projectiles already. The hypotenuse is going to be the combination of velocity of the swimmer relative to the ground. And we can get that by doing 6 squared plus 2 squared equals this squared, and then take the square root. So let's do that. 6 squared plus 2 squared, take the square root, and we get 6.3 meters per second. So I'm actually swimming faster, just like I was walking faster in this example. I'm actually swimming faster relative to the ground because I have my speed and then I have the water speed, and they don't add, they combine, and they combine in such a way using the Pythagorean theorem. It's not a velocity until we give it a direction, so we need to get the angle. So we can do tan theta is 2/6. Theta is going to be the inverse tan of 2/6. And I get about 18 degrees, I think. Yep, let's say 18 degrees. So even though I go to swim straight, the river carries me over. I wind up swimming at an 18-degree angle that way. You might have noticed this at the beach. You go to swim, you're like, there's my blanket and my umbrella, I'm going to swim in, and you swim, 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 swim. You aim for the shore, and then you get there and you're like, where's all my stuff? And you didn't realize that the ocean was traveling to the side. And so you actually wound up going at an angle and wound up down shore from where you intended to go. And then you have to walk back. And that's really a real life example of how this always happens and how you know why it happens. You can also figure it out. You can also be extra clever and figure out at what angle should I aim so that I don't have to walk back to my blanket. Can I swim this way? You know, if you kind of aim this way, maybe you could cancel out the effect of the water and wind up going straight. And that's the last thing we're going to figure out. Now, it might seem on like the surface, oh, I just have to aim 18 degrees the other way, and that's going to take me over to the side. But it's not quite as simple as that. So we have to work it out. Let's let our little transitive property thing here be our guide. It's going to help us sort through what's a somewhat subtle situation, which is what happens if I want to go straight. So let's look at that. Let me erase all of this business right here. Okay, so in fact, I'll leave that up for reference. So now let's say I have same river, right? I want to swim. My river is still traveling. Let me draw it little up here. My river is still going. The velocity of the river relative to the ground is 2 meters per second that way. I also know that I can swim at 6 meters per second. So whatever direction I aim in, it's going to be 6 meters per second. That's what's different. I'm aiming at an angle, so I'm going to make the hypotenuse of a triangle with my body, and that's going to be 6. Whereas here, the hypotenuse with 6.3, we're going to have a different triangle where the hypotenuse is going to be the speed of u relative to the water. Now we can work this out kind of conceptually, but let's actually think about it a little bit rigorously first. Velocity of u relative to the water, relative to the river, plus the velocity of the river relative to the ground. And again, these are not straight additions, these are vector additions, equals the velocity of u relative to the ground. This direction I want to be straight across. I know the velocity of the river relative to the ground is that way, which means I'm going to want to aim so that I cancel out this horizontal motion. I want the x component of my velocity to be like the treadmill and be totally canceled out by the motion of the river. So all I have left is that forward motion across the river. So my velocity is going to be something like that. Let's try to combine these and see how it works. So I'm gonna have, and here you have, it's gonna look like a funny triangle. It's not gonna look like this, and that's okay. I have the velocity of me relative to the river, which is 6 meters per second because that's my speed relative to the water. I want to set it up just right so the velocity of me relative to the ground is over here. Velocity of you relative to the ground is going to be straight, which means that the velocity of the river relative to the ground is going to form the leg of that triangle. So the part that's the same is the velocity of the river relative to the ground. The parts that are different is that I'm aiming with my velocity at an angle here. And so the velocity of me relative to the ground is going to be less than my swimming velocity, whereas here it was more. So let's figure this out. I can still, you'll also notice the arrows don't go the same way. When I have a vector like that, the vectors you add to get it always go in a line. Here, I'm not adding this vector and this vector. I'm saying velocity of me relative to the river plus the velocity of the river relative to the ground is the velocity of me relative to the ground. So I'm adding this vector plus this vector to get this vector, the angle vector plus the sideways vector to get the up vector. Okay, let's do our Pythagorean theorem in reverse. This was 2 meters per second. So I have 2 squared plus this squared equals 6 squared. So if I do 6 squared minus 2 squared and then take the square root, I get 5.7. So here I actually wound up wasting some of my velocity to counteract the river, and my overall progress across the river is less, 5.7 meters per second. And now let's get the angle. So I'm going to use tangent again. Tangent theta is 2 over 5.7. So inverse tan of 2 divided by 5.7. And I get, what do I get? Let me see. Tan theta is 2 over 5.7. So inverse tan of 2 divided by 5.7. I get 19 degrees. So whereas here it was 2 over 6, and I got 18 degrees. Here I have 2 over 5.7, and I'm going to go at 19 degrees. So it's not quite the same angle. Okay. So let's see what else. I think that's it. So this is actually really cool. If you watch planes landing in crosswinds, you'll notice sometimes, though you have a crosswind and the plane wants to come in straight at the runway, but in a crosswind, they have to aim against to cancel out the effect of the crosswind. So you see these planes coming in sideways, but they're like coming in and landing straight. And it's really cool. That's one of the fun things. When you know a little bit of physics, it becomes even funner to go to the airport and watch planes land. Someday we'll be able to do that again. All right, guys, that's it. I hope this was a little bit helpful. You'll have some practice with it, and you can refer back to this. Have a great night and see you later. Bye.